Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 4.6, Other Trig Graphs. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. Today we're going to look at building the four remaining trig function graphs, the tangent, the cotangent, the secant, and the cosecant, based on the prior knowledge of the sinusoid graphs, and analyze those graphs because they are the quotient or reciprocal functions of the sinusoids. And we will also analyze these graphs based on domain restrictions, one-to-one functions, and inverses, so that we can then determine the graphs of the inverse trig functions. We'll begin with taking our prior knowledge of the sine graph, and we will sketch it. So I'll do the sine graph in green. I'll do it lightly. And we'll just start off recognizing our scale is still pi by 6, so the x scale, every space is 30 degrees or pi by 6 radians. And I'm just going to put a tick mark for the quadrantal angles so that it doesn't get too crowded. So 6 pi by 6 is pi, a little bit more than 3. 1, 2, 3, we have 3 pi by 2, and we have 2 pi, just a little bit past 6. And going back 3 spaces is negative pi by 2, back 3 more is negative pi, back 3 more is negative 3 pi by 2, and back 3 more still is negative 2 pi. We can see some boundary heights of 1 and 2. We can also see the square root, the 1/2 and the square root of 3. I haven't put the 1/2, and this is root 3 over 2. I haven't put the root 2 over 2 line in. And we have the reciprocal of, I'll just do it in highlighter for a moment. The reciprocal of 1/2 is 2, and the reciprocal of root 3 over 2 is root 2 over 3. Okay, so I'll erase those, and we'll go back to plotting the sine graph in green. So we have 0, 0. We have a maximum at pi by 2. On the sine graph of 1, a 0 at pi, a minimum of negative 1 at the angle 3 pi by 2, and a 0 at 2 pi. We also have these other angles. I'm not bothering putting in pi by 4 here, so I didn't put in the square root 2 over 2 line. Okay, we continue on, filling in the rest of the values. And graph paper like this makes it very easy to plot the sinusoid. Okay, we have our minimum, zero, maximum, 0. Okay, so we have 2 periods or 2 cycles of the sine graph here. Now what we're going to do is recognize how do we transform the sine graph to get the cosecant graph. Well, if we recall by definition, the cosecant graph is r over the second coordinate on the unit circle, so it's the reciprocal of the sine function. The change that we are doing, the reciprocation, is after the basic sine function has been acted on x, so the reciprocation is a vertical change, not a horizontal change. And so what we mean by that is that the angle is not, the input, the angle is not changing, but the sine ratio, or the output, or the y-coordinate on the graph is changing. So if we have a point on the sine function, let's let f of x equals sine x. Then we have a point f of pi by 6 is equal to 1/2. And we will let g of x be the cosecant function. So then g of pi by 6 is going to be 1 over f of pi by 6, which is 1 over 1/2, which is 2. So what we're going to do is take each of the plotted points from the sine curve, and we are going to reciprocate the y-coordinates to get the y-coordinate on the new graph, the cosecant x. Reciprocation is not one of the basic transformations of reflection, scale, or translation that we have talked about in the past, but it is a transformation nonetheless. So let's take this maximum point. When the angle is pi by 2, sine of pi by 2 is 1. The reciprocal of 1 is still 1. So the same point for the maximum on the sine graph is also a point on the cosecant graph. We can say that this point then has a y-coordinate of 1 when x is negative 3 pi by 2, and so it's still the same point on the reciprocal graph. Meanwhile, when the y values are negative 1, the reciprocal of negative 1 is still negative 1. So these 4 points are points in common between the sine x graph and the cosecant x graph. Let's take the points now that have a height of positive 1/2. For these different x values, or angles, the sine ratio of 1/2 can be reciprocated to a ratio of 2 over 1, and so those become points on the cosecant graph. Similarly, when the heights are negative 1/2, the reciprocal of negative 1/2 is negative 2. And so we have a few more points plotted just from the basic knowledge of the sine graph to get the cosecant graph. The other point that's a little lower than a height of 1 has a height of square root 3 over 2. And the reciprocal of square root 3 over 2 for the same angle gives us the cosecant of pi by 3, which is 2 divided by the square root of 3. And that's the same thing here. And this point gets reciprocated, rather this point gets reciprocated here, this one here, and so forth on the other side of the x-axis, of the y-axis. Last but not least, when the green sine graph has x-intercepts, that means that the height of the graph, or the y-coordinate, is 0. Reciprocating 0 gives us 1 over 0, which is undefined. So whenever the sine x graph has an x-intercept or a 0, the cosecant x graph is undefined and therefore has a vertical asymptote. So these vertical asymptotes are very useful for guiding the shape of the cosecant graph. And we see that the vertical asymptotes repeat just as often as the x-intercepts of the sine x graph repeat. Namely, every pi radians, the sine x graph has a 0, and the cosecant x graph has a vertical asymptote. And without plotting more points, we can see the basic shape of the cosecant graph looks like this. Now, while each of these branches of the cosecant graph look like parabolas, they are not parabolas. Mainly, we know that a parabola graph is not bounded between two vertical lines, but continues to get wider. Secondly, we know that a parabola graph comes from a quadratic equation, and cosecant x is not a quadratic or power function. So it is incorrect to say that this shape is a parabola shape. Okay, it's bowl-like or U-shaped, but not parabola-shaped. Now let's take a look at the table and complete it for the analysis of the functions. We can talk about the zeros and the vertical asymptotes as x-coordinates that make y either equal to 0 or y undefined. We can do this for x values on a restricted domain, such as from negative 2 pi to 2 pi, or we can talk about the values for all reals. In this video, I will just talk about the zeros from the graph, therefore on the restricted domain from negative 2 pi to 2 pi, and we will generalize to all of the formula for the coterminal angles later on. So the zeros are the x-intercepts of the sine graph, and the green zeros occur at negative 2 pi, negative pi, 0, pi, and 2 pi. And I might run out of room here. I'm going to write the zeros. We could talk about these as ordered pairs of points. Negative 2 pi, comma 0, or negative pi, comma 0, or 0, 0, or pi, comma 0, and I don't have enough room to put or 2 pi, comma 0. We can already start to see that the zeros of the sine x graph occur at the integer values of pi. So we could call that n pi. We'll write that later. We know that the sine graph is continuous on its entire domain, therefore there are no infinite discontinuities and no vertical asymptotes. So I'm just going to write none. The domain as a result is the set of x values that makes y defined, and the domain is not restricted in the case, or has no problems, so this domain of sine x is x contained in the reals. The restricted domain is the set of x values that we choose on which to make the sine x graph 1 to 1. And based on our guidelines, that we want to take as much of the graph as possible, that we want to take a segment of the graph as close to the y-axis as possible, we are going to choose this segment of the sine graph from negative pi by 2 to pi by 2. And this is going to help us later on when we come up with the graph of the inverse sine function. So the reason for restricting the domain is that when we now look at this segment of the sine x graph, it's always increasing, or it may in some cases be decreasing for different functions. But the purpose of choosing this portion is that we have now created a subset of the original function, which is 1 to 1. And as a result, we can reflect this graph through the line y equals x to get the inverse trig function. We'll save that for later. Continuing on in the table, we want the range, the amplitude, period, and the interval of continuity for the sine graph. The range is the set of y values, and because the sine function is based on the opposite length over the hypotenuse length, and the hypotenuse cannot be exceeded, we have that the sine function is bounded from the heights of -1 to +1 inclusive. So y is contained from -1 to +1. The amplitude is the distance from the baseline to the maximum or minimum. So the basic trig function, the basic sinusoid, has an amplitude of 1. The basic period is 2 pi. It takes 2 pi radians before the graph repeats. And the function is always continuous on the domain. So it's continuous on x contained in the reals. Now let's go and take a look at the cosecant graph. The zeros, or the x-intercepts of the blue cosecant graph. Well, we notice that the blue cosecant graph never gets within this green region. I'm going to highlight where the sine graph lies. And in this green region, the cosecant graph never exists, or there's no y values defined in this green region. And so we're finding that, there we go. Let's take a look at the question again. To come up with the zeros, we see that the height of the blue graph is never 0. It never crosses the x-axis. And we will say then that the zeros are none. This is consistent with the fact that the sine graph has no vertical asymptotes. Similarly, the zeros of the sine graph become the x-coordinates of the vertical asymptotes. And there are infinitely many vertical asymptotes for the cosecant graph. Now these are not all of them. We will later on generalize and get all of the real values for the vertical asymptotes. The domain is the set of x values for which the function is defined, or the y value is defined, and the y value is undefined, or non-zero over 0, at these x values. So we need to exclude these values from the domain. Well, at this point, actually, I am going to generalize because it really makes it easier to write all of these infinitely many values in one statement. We see that these x values are the n pi's, and so x is contained in the reals, and x is not equal to the n pi's. Now we do need to specify what kind of number n is. And we know that n is an integer. The restricted domain is the subset of the domain of the cosecant function on which the function is 1 to 1. And it's not so difficult to see it's related to the restricted domain of the sine function. However, instead of going directly from negative pi by 2 to positive pi by 2, we know that we have a missing value in cosecant's domain at x equal to 0. So our restricted domain for cosecant x goes from negative pi by 2 to 0, or 0 to pi by 2. This is the portion of the original domain on which the cosecant x graph is 1 to 1, and it will help us to draw the graph of the inverse cosecant x function. So we have x is contained from negative pi by 2 to 0, excluding 0, union 0 to pi by 2, including pi by 2. The range is the set of y values, and as a transformation, the y values on the sine graph have been reciprocated to get the y values on the cosecant graph. Therefore, the range has been reciprocated, or in effect has been turned inside out. The range of the sine graph is all of the green band from -1 to 1. The cosecant x's range is everything else. So when y is less than or equal to -1, or when y is greater than or equal to +1. So y is contained from -infinity to -1, inclusive, union 1 included, up to, but not including infinity. The amplitude doesn't make sense in the case of a cosecant x graph because there is no maximum distance away from the baseline or the kind of the midpoint line. And so we'll just say not applicable, or none. The period does apply, however, and one cycle of a cosecant graph is 2 of these bowl shapes, which takes 2 pi radians to complete. And so as a general rule, a function and its reciprocal have the same period. The function is continuous wherever we don't have the vertical asymptotes, and it happens to be the same as the domain in this case. So x is contained in the reals, and x is not equal to the n pi, where n is contained in the integers. Since we've actually generalized this, maybe I'll go back and put the zeros in. The zeros are located for the sine function at n pi for x, comma y for 0 for y, as long as n is an integer. Similarly for the vertical asymptotes. The vertical asymptotes occur at x equals n pi, where n is contained in the integers. Okay, I'm going to leave exercise 2 to draw the graph of cosine x and its reciprocal secant x, as well as completing the table of values as an exercise, or rather the table for analysis as an exercise. We will take a look then at generating the tangent of x graph, not as a reciprocal of another function, but as a quotient of 2 sinusoids. So what we're going to do is lightly sketch the sine x and the cosine graphs, and from that use the sine xy coordinate divided by the cosine x coordinate for each different angle to come up with the quotient tangent x coordinate. So I will do my sine x graph in green lightly, and I'm putting in my quadrantal angles and their ratio values first. So here is my sine function. I think this is a height of 1/2 here. And so we have this value. Again, the more angles we plot, the easier it is to come up with the appropriate shape curve. Okay, so there's the sine x graph, and I'll just indicate that I've sketched it in green. And I will use yellow, if it's not too hard to see, for the cosine graph, which, as we know, is a horizontal translation, pi by 2 to the left of the sine graph. So it come down here. Okay, so we can see that these two graphs are horizontal translations of each other. I'm just going to tidy up this portion of the graph. And now we want to take, for each angle, so for each vertical line, and I'll demonstrate by highlighting one of them. Maybe I'll take this angle here. The angle for which the sine x and the cosine x are the same is the case of the 45-degree reference angle. And we have, when the angle is 45 degrees, or pi by 4 radians, sine of pi by 4 is root 2 over 2. And the cosine of 45 degrees is also root 2 over 2. Therefore, something divided by itself, or root 2 over 2 divided by root 2 over 2, tells us that the tangent of 45 degrees is 1. And so I'm going to draw the tangent graph in blue. And at 45 degrees, the tangent of the angle is 1. We can see when the two graphs intersect again is over here. And if I draw this line, if I'm going to be clear about the quadrants, I can see that from 0 to pi by 2 radians is quadrant 1. From pi by 2 until pi radians is quadrant 2. From pi radians until 3 pi by 2 radians is quadrant 3. And from 3 pi by 2 until 2 pi radians, we have quadrant 4. And so we know that in quadrant 1, the tangent of the angle will be positive. In quadrant 3, sine of 225 degrees and the cosine of 225 degrees are both negative square root 2 over 2, which means that the tangent of 225 degrees will be positive 1. We know that in quadrant 2, with a reference angle of 45 degrees, so here's 90 degrees, and here is 180 degrees, so halfway in between these two lies here. So that is another 45-degree reference angle. So the sine of 135 is positive root 2 over 2, and the cosine of 135 degrees is negative root 2 over 2. Therefore, the tangent of 135 degrees is negative 1. So along here, the tangent is negative 1, and the same will be true in quadrant 4 with a reference angle of 45 degrees. So halfway between 270 degrees and 360 degrees, we have our 45-degree reference angle, and the ratio for tangent is either positive or negative 1. In quadrant 4, the tangent of an angle is negative, so we get negative 1. We're not going to plot a lot of points. These are 4 good anchor points, but we are also going to take a look at what happens in the quadrantal angles. So at 0, sine of 0 is 0, cosine of 0 is 1, and the tangent of 0 is 0. So we have an x-intercept. We also have an x-intercept the next time the sine function is 0, because the y-coordinate of the sine function is 0 divided by negative 1 for cosine of pi. The quotient is 0. And so what this tells us is that since the tangent is the quotient of something over something else, the zeros of tangent are the same as the zeros of the numerator. So tangent x and sine x have the same x-intercepts. So I'm going to take all my green x-intercepts and make them blue as well for the tangent graph. Now whenever cosine x has zeros, the sine x has either a maximum or a minimum. And so whenever cosine x has a 0, the tangent function will be non-zero over 0. And as a result, the zeros, or x-intercepts of the cosine graph, will be vertical asymptotes of the tangent graph. So every time I have a yellow x-intercept for the cosine graph, the tangent graph in blue has a vertical asymptote. And here are the vertical asymptotes for this particular grid, and we can draw the graph. So we have x-intercept here. I missed the minimum and, the negative 1 and positive 1 values over here, so I'll just backtrack in between. We have negative 1, we have positive 1, we have negative 1, and we have positive 1. And if you wanted to plot more points to get the graph more accurately, you could do, but here's the basic shape for the tangent graph. Okay, so maybe I'll highlight that so we can see it a little bit better. The tangent graph is highlighted in turquoise. Okay, each one of these branches should have arrows on the ends. And we can see that there is a periodic behavior, but the period is different because we have the cycle repeats between every two vertical asymptotes, and the vertical asymptotes are at the same place as the zeros of the cosine, which occur every 180 degrees, or pi radians. So we see that this is one cycle, and one cycle corresponds to pi radians, which is different from the sinusoids. All right, we're ready to fill in the table to analyze the function. And again, as a recap, we have that the zeros of the sine function occur at the n pi values, where n is an integer. The zeros of the cosine occur at the odd pi by 2's. So for example, here and here. This is 1 pi by 2, this is 3 pi by 2, this is 5 pi by 2, this is 7 pi by 2, etc. So the zeros of cosine are at the odd 2n plus 1 pi by 2's with a y-coordinate of 0. I don't have room to write n contained in the integers. Please know that the n is an integer. The sine function has no vertical asymptotes, neither does the cosine function, and the domain for each is unrestricted. It has no domain problems. In other words, you can take the sine or cosine of any angle, quadrantal, non-quadrantal, principal, coterminal. There's no restriction. In this sense of restricted domain, we're talking about the set of x values that we want to restrict the domain to, so that this function will be one-to-one. And we saw earlier that this domain is restricted to negative pi by 2 to pi by 2 for sine x. And for cosine x, we see that the restricted domain will be from 0 to pi, following the three guidelines. Now, to take a look at the zeros of tangent, tangent does have x-intercepts or zeros. They are the same as the sine function's x-intercepts, so n pi comma 0. And tangent also has vertical asymptotes. Because tangent is a quotient, whenever the denominator only is 0, tangent will be undefined. So tangent has vertical asymptotes at the odd pi by 2's. The domain excludes the vertical asymptote values, so x is contained in the reals, and x is not equal to 2n plus 1 times pi by 2. Recall that the domain is the set of x values that makes y defined. When x is these values, the cosine x is 0, but the sine x is not 0, so the tangent quotient is non-zero over 0, or undefined at these x values. The restricted domain is the portion of the tangent graph that includes as much of the graph as possible, so we would want to take an entire branch. We want to be as close to the y-axis as possible, and that would give us the branch from negative pi by 2 to pi by 2 for the restricted domain. So I'm going to highlight that in green for the restricted domain, but I'm going to use a thinner line. But we cannot include the endpoints for the restricted domain because the endpoints are where we have vertical asymptotes of the tangent graph, and those x-coordinates are already excluded from the domain of the function. So the restricted domain, for which the tangent x graph is 1-to-1, is almost the same as the restricted domain for sine x, except not including the endpoints where there are vertical asymptotes. The range is the set of y values on the tangent graph that are produced, and because of these arrows we see that y is going to negative infinity and to positive infinity. We can think about why that is from the definition of the tangent function being the opposite over the opposite over the adjacent. And our fourth domain restriction states that the hypotenuse cannot be exceeded. And if the hypotenuse cannot be exceeded, but it is not part of the definition of the tangent function, we ask, is there any restriction on how big the opposite side of a triangle can be compared to the adjacent? Or, on the unit circle, if we were looking at ordered pairs, if we have a point x comma y, is there any restriction on what the x value can be compared to the y coordinate? Well, we remind ourselves that the only restriction is what the radius can be, so x and y can be anything. The opposite and the adjacent can be anything with respect to each other, and therefore there's no restriction on the output or the tangent of an angle for this function. Again, amplitude is the maximum distance away from the baseline, and since there is no maximum distance as y approaches negative infinity or positive infinity, there is no amplitude. The period, it takes pi radians to complete one cycle, and the function is continuous wherever it does not have a vertical asymptote. So it's continuous on the domain again. And the domain excludes the odd, that should be not equal to, excludes the odd pi by 2's or the 2n plus 1 pi by 2's. I'll let you continue with exercise number 4 on your own by looking at the cotangent x graph either as a quotient of cosine divided by sine, cosine x divided by sine x, or as the reciprocal of the tan x graph. Just to go back and take a look at the tangent x graph from the point of view of quadrant 1 and 3 being positive and quadrants 2 and 4 being negative, we see in quadrant 1 that the tangent x graph lies above the horizontal axis. In quadrant 2, the turquoise tangent x graph is negative. In quadrant 3, from here to here, from x-intercept to vertical asymptote, tangent x is again positive. And in quadrant 4, from vertical asymptote to x-intercept, the tangent graph is negative. So we should be very consistent with our sign chart, as well as, I don't want to clutter up the graph too much, but if I did some shading, we could see how the sign chart would work here. For the tangent x graph, the graph lies above or below the x-axis according to the definition of sine x over cosine x, or opposite over hypotenuse and adjacent and hypotenuse, for example. Well, that concludes taking a look at the reciprocal and quotient functions. We will continue in a separate handout to look at the inverse trig functions. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.